just a reminder about what we did last week. We define what is an attracting set. It's a closed set such that over the evolution, points are approaching omega, so lambda. So the attracting set lambda is such that all points approaching lambda generate an open set. This is a definition. And we call this set of points which approach lambda over the evolution the basin of attraction. And how do we find attracting set? There is a nice notion which is called the trapping region. A trapping region is an open set which, so it's open set X such that over the evolution, its boundary enter the set. So I made a picture. You take an open set, you look at its boundary. So this is a boundary when I take the closure. And as soon as t is bigger than 0, the points of the boundary have to be inside. So this is a trapping region, the definition of a trapping region. And it turns out that if you take a trapping region, then the limit, its limit set is attracting. So this is a way to get attracting set. And we work on one example. Okay. And unfortunately, this notion of attracting set is not, or attracting region is not good enough for the following reason. If you have a trapping region and if X is a point in the limits, a fixed point in the limit set, and we have seen an example, then this unstable set is also inside. And what happens is when you have a fixed point, you leave this fixed point with a velocity equal to 0. So that's why in this region, in this basin of attraction, it should be a small omega here, I suspect. Let me just check. Yeah, sorry, it's a small omega. In the attracting set, we have those points which are not attracting, but they are coming because of a 0 velocity. So it's an annoying subset of this attracting one. So we add one more condition. And I define this notion of topological transitivity. It's a nice notion which appears in many places. Consider two sets, and we have this notion of topological transitivity if when you evolve one of these two sets, at a certain point, it will touch the other one. So we will assume that what we are going to call an attractor has this property of topological transitivity. It's a kind of mixing. So over the evolution, this set will suddenly touch V. So we call an attractor, not only it's a attracting region, it's a closed invariant attracting region, but we also assume that it is topologically transitive, so it has this good property. And on an example, I show you an example where this property is not satisfied. That's why we don't call it an attractor. Then I mentioned the Lorentz attractor, which is quite famous, but unfortunately, I don't think we have shown that it's topologically transitive. But it's not essential, because this is one way to define an attractor, but there are equivalent definitions or other definitions very similar, and then this one fits into the other definitions. Then we quickly went to stability. So the stability around a fixed point is quite easy to understand, because what you can do, you can always linearize a system with a Jacobian matrix. And once you have this Jacobian matrix, you can study its eigenvalues. And we say that this fixed point is hyperbolic. This is a nice case if the Jacobian matrix has no purely imaginary eigenvalue. So all have a real part, which is not 0. And for hyperbolic fixed point, there is a theorem which said that the flow around a hyperbolic fixed point is in fact essentially the linear flow. So the linear flow is a good approximation. You just need to deform a little bit the space, but essentially the same as a linear flow in a small neighborhood or in a small open set containing a hyperbolic fixed point. And there is a picture in the notes. Of course, it's a very local information, but it's sufficient. And I just mentioned at the end this notion of heteroclinic orbit or homoclinic orbit. It's when you have two fixed points. Heteroclinic one is when one orbit goes from one fixed point to another one. The homoclinic is when the fixed point is the starting point and the ending point of an orbit. Okay. And they play a role at different places. All right. So we are going to continue with stability, but now no more around a fixed point, but around a periodic orbit. Unfortunately, this part is a bit long, but it's quite interesting. And then we move to a different topic. Is there any question, or do you have any question? Okay, so let's, as I said, we study the stability. So the framework is still we are still in the continuous setting. We will move to the discrete time setting later. But so let me remind you the framework. So we consider, I just remind the framework because it's not on the blackboard. So M is a subset of Rn. So we are in this case, F is a once differentiable function on M is value in Rn, and we consider the differential equation x dot of t is f of x of t. And we associate to this a flow, which I have denoted by omega, which is defined on R times M with value in Rn. I call this W. And I assume the flow is complete. That's why I can take all time. All right. And now we let gamma be a periodic orbit. We have seen one example, and there is a picture. So it means we have one in Rn, we have one set where all points are just going from this to themselves. So what means a periodic orbit? It means there exists a capital T bigger than 0 such that phi of T plus capital T for x is the same as phi of Tx. I should mention x is a point here. It's not an arbitrary point. It's a point on this periodic orbit. It's a capital T periodic orbit because we come back to the same place every capital T. Right? And probably I will call this x0 just to make it a bit special. X0 just to make it special. So this is a framework, periodic orbit. And now we would like to study, many things can happen. For example, a periodic orbit can be attractive, so all trajectories would convert to it, or it can be repulsive, it can be attractive inside or repulsive. So this is what we would like to understand. Of course, if you are just on gamma, you stay on gamma, but if you are a bit away from it, what happens? This is what we would like to study. So for just one point, as I said, we can use the linearization, but for periodic orbit, we need to develop new tools. So this is a framework, stability around a periodic orbit, and you will see it's a nice theory. It's just a bit long. Let's try to do it. So the first thing we are going to define, this is example. I'm going to define a hyperplane sigma, which is perpendicular to the curve at x0. I will give an equation later. So let's see sigma be a hyperplane perpendicular. It's perpendicular to gamma, perpendicular to gamma at x0. Why is it a hyperplane? Because you have one direction here, so the hyperplane is of dimension n-1. And what we are going to do is we are going to take a x close to x0 on this hyperplane. We will let it evolve and see where we get, where we arrive. Of course, it might be possible that we will move away, but in this case, I mean, we will see that there will always be a small neighborhood where we really touch again the hyperplane. So for any x belonging to this hyperplane, I assume that x, I'm not very precise, but it's close to x0. We will be more precise. So I don't want to take an x which is too far away. I take an x which is not too far from x0. We set p of x as the first intersection of the flow phi tx with sigma, or t bigger than 0. So this is exactly this picture. I take a x, I let it evolve with the flow, and this is going to be p of x, if it exists. Of course, if it goes away, there will be no p of x, but if it intersects against sigma, I call this point p of x. And so let me just give a name to this. In a few minutes, I will be a bit more precise. So definition, this function or this map, I call it map, from, so V, what is V? V is a small set on sigma. It's a small set on sigma which contain x0. So this is a V. Again, I will be a bit more precise. V is, it's an open set on sigma containing x0. So this function, which associates to any x its image after a certain time, but when it hit against sigma, is called the Poincaré map. It's called the Poincaré map. So now I need to be a bit more precise about how to define it. But there is just first an observation. I will not be more general, but in some cases, it might be important to consider not hypersurface, but something a bit more general, like a more general surface. And you can also do it as long as you give a definition of this surface. You can take one point on it and check when you are back to this surface. So it has not to be a hyperplane. You can do it more generally. But I will not do it. But yeah. And it has, as long as what you have to avoid, of course, you have to avoid a surface which would be tangent to the plane. This is tangent to the curve. So you need something which has a non-trivial intersection with the curve. But again, I will not be so general. Okay. So now I want to define this more generally, and there is a theorem which is going to help me for this. This theorem is based on implicit function theorem, which you will see, or we have seen in Calculus 2, yeah, a long time ago for some of you. And I'm sure you remember. If somebody wants to look at the proof, it's a nice theorem. So it would be a good report if somebody want to work on this. So let me state it. We are in this, okay, in this framework, I don't repeat the framework. In the note it's written. But I write the equation for the plane sigma, because I have not written it yet, is a set of x in Rn. Probably you know the definition of a hyperplane. This is the equation of this hyperplane. Why? Because we have here the vector x dot at 0, the derivative at 0, but the curve, we have this relation. So it means the tangent vector is equal to f at x0. That's why we want to have this vector perpendicular to the hyperplane. So this is the definition of the hyperplane. It's a set of points such that the scalar product, okay, it's not written. The scalar product between x minus x0 and f of x0 is 0. This is the definition of this hyperplane. So now we have it. So in this framework, which is written here with this definition of the hyperplane, let me keep this. So what is the statement that exists? Delta bigger than 0 and a function which I'm going to call tau. It's a C1 function, so once continuously differentiable, defined on so it's a function defined on a small ball around x0. This is a ball of radius delta at x0. It's a function with value in R plus. It takes, you should think about tau. I use it on purpose. T is for time. Tau is for time. So it associates to the point x0 the time t, and such that we have this relation phi of tau of x belong to sigma. So look at this. What does it? Remember, this tau should give you a time. This tau of x gives you the time when you let the evolution, the point x is back to sigma. So it tells you take any x in this ball, let it evolve, and at time tau of x, you are on sigma. So this function gives you the time you need to go from an arbitrary point x in this ball back to the plane sigma. So this is the definition of this function. And the proof of its existence is nothing but implicit function theorem. So once you have this, now we can define the Poincaré map more precisely. So with this, we can then define. So look here, I was not very precise. I just mentioned a certain open set. Now with this theorem, I can be more precise. P, we can define it on this ball of radius delta intersection with sigma. And so this intersection is what I had defined before. So it is this with value in sigma. And how we define it, P of x is nothing but phi of tau of x. Because it gives me exactly the first time I reach again the surface. You have a question? There is a mistake.
That's why we need this part to be C1.
No, we don't need it. It's for free. It's for free in the sense I started with a f which is C1. And if you look carefully at the implicit function theorem, you keep the same class of regularity. You don't lose anything. So I need C. I can probably be a bit tweaker because we have seen some existence theorem for Lipschitz. But I said C1 is easier. So I started with C1. And by the implicit function theorem, for free, I get C1 here. So I don't have to impose it. Second question? All orbits would, the first intersection, it's unique. Of course, and you know, this is why this is important. If you remember the implicit function theorem, it's only a local description. And this gives you the area you look at. Of course, if you continue, you might go a second time. But then it would not be a continuous function compared to this condition. So you would be back on a different layer, on a different place. So this localizes you around this point here. Because this point, you know it takes exactly, it's on the periodic curve, you know it takes exactly capital T to be back. So this is important in your implicit function theory. Okay. So now I have defined this more precisely with this open set intersection the plane or the hyperplane and the point, this point on the sigma plane, on sigma, is given by this.
The ball and the sigma, it's only on one point.
No. Take a ball, intersect it with a plane. It gives you a disk, thank you, in any dimension, or hyperdisk.
So we have to contain x as well.
X0.
Not just x0, but x.
No, x is any point on this hyperdisk.
Oh, okay. Right.
I don't fix it. The only point which is fixed is the initial x0. Now, I observe that I already mentioned it. Sigma, you can identify it with a plane of dimension n-1. So it means that T, which is, you can consider it as defined on the ball of radius delta, x0, intersection Rn-1 to Rn-1. You just take coordinates of our plane, and your plane will be the same as Rn-1. So what does it mean? It means it's a function defined on a subset of Rn-1 to Rn-1. So it's a function of n-1 variable. It's a vector field of, yes, it's a vector field of n-1 variable. So its Jacobian matrix is a matrix of size n-1 times n-1. So this is important. So it means, it implies that the Jacobian matrix, so it's a matrix of first derivative of T, it belongs, I will define it at x0. At x0 is a matrix of size n-1 of R. I emphasize this because it means we have n-1 eigenvalues, which is not so surprising because you are in this plane of dimension n-1. So you have n-1 direction. Okay. So this is the first part of the construction. We define this Poincaré map as a function on this hypersurface defined on a hyperdisk with value on the hypersurface. So this is part of the story, and we will come back to it in a few minutes. Is there any question or remark? Now I want to do something else, and then we will link these two things. So we consider, so for the periodic orbit, I'm going to I define a new thing. I define ht of x as the Jacobian matrix of okay. So what is it? You know, phi is a function of time and space. If I forget the time dependence, it's a function of space. So I can take its Jacobian matrix. I just take the derivative with respect to space. And once, or in the notes at least, I mentioned when I put the t here, it means I just concentrate on the other variable. It's still a so I'm using different notation. Phi of tx, sometimes I can, or sometimes it's useful to write it like this. It simply means I concentrate on the x variable. And this is what I do here. I define this H, it's a matrix, as a Jacobian matrix with respect to the x variable of this function. Okay, I give this definition. For a point on this periodic orbit. So I can do it at x0, but let me just do it at x and any point on this periodic orbit. So remember, H is a for each, this is a matrix. This one is a matrix. It's an m by n matrix for all t, for any t. And now there is a small exercise for all of you. I did my homework, I did it, but I let you do it. So remember, we have this equation. This is just our initial equation. We get, take the derivative with respect to t of h of tx. So now, this is still a function of space and time. I take its derivative with respect to time, and I'm claiming, and you can do it, this gives you it's an exchange of two derivatives. You have to be a bit careful. You get this equation. It's not completely trivial. You need to work a little bit. Remember you need calculus too. The derivative of a composition, it's related to the composition of the Jacobian matrix. And you use this equation, you obtain this. So what it is, the derivative of this function with respect to t, it's a matrix, is equal to, this is a matrix, the Jacobian of f evaluated at this point, times, this is the internal derivative, times this h of tx. So this is a product of two matrices, both belong to Mn of R. So you have an equation of this type. Again, it's calculus 2 plus this relation. So now, if we fix x equal to x0, so if I now look at the point x0, which was my initial point. I guess it's arbitrary. We have one more thing. We have phi of t plus t x 0, as I already mentioned. This is by periodicity. Moving along this periodic orbit by capital T, you are back to the same point. But it implied that this implies that now if I look at this Jacobian matrix of phi of t plus t x0, phi of t plus t x0, this is the same as this. This is clear. Because of this relation, the argument is the same. So what we end up with this h, I use dot for derivative with respect to time, is t evaluated at tx is equal to a certain matrix, which I'm going to simplify the notation. What is this A? This is the A. I just simplify the notation. This is A of t. And I do this at x0. Otherwise, I would have a dependence on x. And the same, sorry, here we have a x0. And what is the property of A? I just mentioned it. With A of t plus capital T is A of t. Oh, this should remind you something. Long time ago, we studied some, in chapter 2 probably, we studied some periodic system. And we had an equation of this type. When we discuss also monodromy, I think it was section 2.8, I'm not sure. We had an equation of this type. It was it's a matrix equation. The derivative of a matrix is equal to a function which is periodic, which is a matrix, applied to this matrix itself. And we have seen the solution. It was part of Floquet theory. I told you it's a bit long, but very soon I will have a nice statement. So we know the solution. So this is a matrix equation. Matrix equation. Everywhere we have matrices with this. And what about h of 0 x0? The definition of h is no more on the blackboard, but if you look at, no, it's no more. This is just identity. Because you had the derivative of the identity function at time 0, and derivative of identity function is just the identity matrix. So I should have mentioned we have this periodicity of A and the fact that the initial condition is the identity. So we get from section 2.8, yes. We have the solution. The solution is h of t x0 is given, oh, yeah, there is a small clash of notation. So let me use a different color. There is a p in the section 2.8, but it has nothing to do with Poincaré, unfortunately. So p of t et of q with this. So sorry, it has nothing to do with the Poincaré. And this is from a result about periodic system. So we had this expression for H. What was it? It's something which is periodic, a matrix which is periodic, which is identity at 0, times the exponential of a fixed matrix. This was what we had obtained for the periodic system. And in this setting, we called h of t x0 was called the monodromy matrix. In chapter 2.8, and you observe that this is nothing but capital T, it's 0 plus t, but it means it's capital T, so P is identity, so this is just E T cubed, which is something I had already written. And at that time, I also called the eigenvalues of this. I just recall some names. The eigenvalues were called Floquet multipliers. I will use just this name in a comment after. And the eigenvalues of Q were called, the eigenvalues were called Floquet exponent. Okay, so this is something we have seen based on this guy H I have defined. So now we have two objects. We have this, which I have introduced here, and this Poincaré map. And for now, they are not connected, but of course, they are both dealing with a periodic orbit. The Poincaré map is going to tell us what happens transversally. And this was also introduced for any periodic system. So the next statement, which is the main one about this, is a relation between these two objects. This object and the monodromy matrix and this Poincaré map I have introduced before. And it gives us completely the stability around the periodic orbit. So I'm going to simplify my life. For simplicity, I will put x0 at 0. I already mentioned this last time. So this is a 0 in Rn. I shift my system so that the periodic orbit has a point x0 at 0. Okay. But this, of course, you can do it without these assumptions. So theorem, I link now these two things. So in this framework, so I recall F is C1 of M, this value in Rn, and phi is the floor of the equation x dot of t is equal to f of x of t. And gamma, the orbit at 0, which is gamma, is a periodic orbit. And now this curly P, not the yellow one, is associated Poincaré map, associated. Okay, so this is what I introduced just before. And still we have the monodromy matrix written there. Then the eigenvalues of this H, so what is called the Floquet multiplier, are 1 and the eigenvalues of the Jacobian matrix of the Poincaré map at 0. Remember, this matrix was n minus 1 times n minus 1. So it has only n minus 1 eigenvalues, and this, which is correct. And the statement is that the eigenvalues of this guy here are 1 and these n-1 eigenvalues of this guy, the Jacobian matrix of the Poincare map. Yes. Why the 1? You can wonder why 1. Simply because the 1 is related to exactly this direction. And then the Poincare map is what happens perpendicular to it. So it's quite natural. Poincare map deals with perpendicular. 1 is this direction, and this is this total dynamical system around your periodic orbit. It's not completely trivial, but it's not so complicated to show this theorem. You need to work a little bit, but you can relate these different objects. Probably once I gave this proof, but I decided to skip it. But this is useful because either now you can compute the eigenvalues of this guy, or you can compute the eigenvalues of the monodromy matrix, and you get the stability. And in fact, I put several pictures in the notes to let me write 1 or 2 sentences related to this. So now, the periodic orbit is asymptotically stable. What does it mean? It means everybody is not everybody. Most of the points locally will converge to it. This is the notion of asymptotically stable. It's attracting. So the periodic orbit is asymptotically stable if all eigenvalues of this Jacobian matrix, the Jacobian matrix of the Poincare map, they lie inside the unit disk. You might be surprised because many times I mentioned in order to have stability, the eigenvalues should have a negative real part. While here I say something different. But if you think it means eigenvalues are complex, but they have to be inside the unit disk of C, so you can wonder what is a relation. But don't forget, we have a relation of this type, which means an eigenvalue which is in the unit circle of the complex plane here corresponds to an eigenvalue of Q, which has a real part which is negative. So this is equivalent to negative real part for the Cloquet exponent for so it's consistent with what we have already seen about the real part of an eigenvalue. To the Lyapunov? No, not here, not here. I don't think there is a real link with the Lyapunov experiment here. No. So what it means, okay. Again, if we look carefully, we can compute these eigenvalues of the Jacobian matrix related to the Poincare map. Look if they are inside the unit disk or outside. And the claim is that the system is attracting. So we have this asymptotically stable orbit if all eigenvalues are inside the unit disk. If they are all outside, I don't want to write it, but if they are all outside, of course, it will be repealing. So everybody would leave this orbit. But then you can have some inside, some outside. And this is why I put some pictures. If some are inside, some are outside, it means it's attracting in some direction or in some subspace. It's repelling in other subspace. And if an eigenvalue has a zero, so it means if it is on the circle or if it has a zero real part when you look at Floquet exponent, you stay, in fact, on a circle around this orbit. So you are in a trajectory which, in one direction, just stay at a constant distance. So it's turning around this orbit. It's difficult to make a picture, but you can easily guess. Right. So this is all what I wanted to say. If you are interested, of course, you can find more in the literature. I gave 1 or 2 references. But now we have a complete picture of these two situations. A fixed point, you need to do the Jacobian matrix around this fixed point, look at its eigenvalue. For periodic orbit, of course, it's a bit more complicated because in one direction, you are simply on the orbit or close to it. Then you have to look on the perpendicular direction. It's a Poincaré map. And looking at the Jacobian matrix of the Poincaré map gives you the information about the stability. Now you can wonder, and there is a remark, instead of this point, if you do the analysis here with a plane perpendicular, do you get the same thing? The answer is yes. Otherwise, there would be a problem. So it means the stability is the same no matter which point you start with on the periodic orbit, of course. Is there any question or remark? I'm not claiming it's easy, and I told you it was a bit long, but it's nice to relate the different piece of information. No question? Clear? Then I'm not claiming that it's easy to compute anything. But at least formally, you know what to do. You have some tools to do something. Probably if you look carefully in the literature, you can find some examples where computation can be done explicitly, and that's probably interesting. And you really learn something only when you do an exercise by yourself. This is the only way to really understand something. So we can now move to a completely different chapter. And we are going to deal a lot with this one. It's called discrete time evolution process. First, I had the title discrete time dynamical system, but I found that it's too restrictive. We will see. So discrete time, I mean, what I want to emphasize is discrete time. And you could think, oh, it's less interesting than the continuous time because physics is more on continuous time, but I think this is not true. For simulations, discrete time is in fact more important because you never have a continuum. So, and the story is different. You cannot just go from discrete time, from continuous time to discrete time. I'm going to say some new things. So it's not just a special case of continuous time. But as I said, I put the title slightly more general than dynamical system. So we will look at different things. And in this case, we shall consider M is a subset of Rn, so as we have done so far, but I also want to consider as a subset of a metric space. So you can wonder why I'm going to introduce this complicated thing. Apologize. In fact, it contains plenty of interesting examples we will see in probably 3 weeks. I want to go in the direction of cellular automaton. And you have certainly all seen some pictures automated, produced by this kind of object. And in order to describe this, I cannot just stay in Rn. I need what is a metric space. So today I just introduced this word. It will be, the definition. It will become more useful in 2 or 3 weeks. And in fact, Rn is part of a metric space. So I could just say with values in a metric space, but let me emphasize Rn as another example. So what is a metric space? It's not a norm space. We have seen, so be careful, it's not the same as a norm space. It's not very different, but we will see there is a major difference. So what is a metric space? It's a set. It's a set I call capital X and a map, which is a metric, and a map D, which take 2 variables in X with value in 0, infinity, such that for any X, Y, Z in capital X, we have 3 properties. And you know these properties because we have seen them already for norm space. So what are these 3 properties? First, the distance between X and Y is always bigger equal to 0. This is already implicitly used here, but more. The distance between X and Y is 0 if and only if both X is equal to Y. So it means you can separate the points. The distance can distinguish 2 points. It's symmetric. So it means the distance between X and Y is the same as the distance between Y and X. That's quite natural if you think about the distance. And the third inequality is a triangle inequality. The third property is nothing but the triangular inequality, which says the distance between X and Z is always smaller than the distance between an intermediate point Y and the distance between Y and X. So these 3 properties are completely similar to a norm space, but what you don't have a vector space. So you cannot add these points. It simply doesn't mean anything. So it means, just a remark, if X is a norm space, it's automatically a vector space, a metric space. Then we can define distance between X and Y as this. And X with D is a metric space. So what do I mean by this? I mean metric space contain the set of norm space. The norm space are here, norm spaces. Metric space are bigger. Any norm space is a special case of a metric space, but the opposite is not true because you don't have the vector space. And where is Rn? Rn is just a small point here. This is Rn. So as I said, in what I M can be either a subset of Rn. It's already included in the bigger set, but it's good to have it. When you consider Rn, of course, if you just consider it as a set, you don't have a norm. But if I'm in this setting, it means I consider Rn with the usual Euclidean norm. You see, this D is very close to what we have seen here because the properties are the same. So in particular, I can define the notion of convergence. Later, we will come to it. When we need really these metric space, I will recall the notion of convergence, but they are available. which is not the case if you don't take a metric. If you just have a set, with points, convergence doesn't mean anything. What does it mean? I'm approaching this point. If I don't have a notion of distance or something, that's it. You cannot define it. Okay. So we will come back to this metric space later, but I wanted to introduce this definition. So now we start with the simplest case, which is a dynamical system. So the 7.1 is discrete time dynamical system. But then I observe this is nothing but the iterated map we already mentioned. So I will recall iterated map. There is nothing more. So let me do it slightly more generally at the beginning. So we consider the semi-group, it's equal either to n or z. You want to have discrete time. Sometimes we have to consider only n positive integers, sometimes all z. I consider M now a subset of Rn. And yeah, that's enough. Oh no, I can consider all subsets of metric space. It will not appear. But if you have in mind Rn, it's sufficient. And I consider W is a set of time and space. And I consider F from W to M with an equation. So it's the discrete analog of what we have seen probably in chapter 3 or 4. So what is the initial equation and the equation? The main equation is x of m plus 1 is f of m x of m. M is an element of G, so it's an integer, positive or negative. So this is the main equation. It should remind, let me just, for comparison, remind you the general case in the continuous setting. And now you should see, oh, there is a big difference between these two equations. You can say, oh, they are almost the same, but in fact, no, there is some issue which plays a role. Look here, we have derivative. So it means if you think about units, f here has a unit of, if it is a position, the derivative would be the velocity. While here, f is related to position. It's at the same level than x. And later, we will see that this small difference plays a role. So just keep in mind, you can, I don't know exactly how to express it, but I think if you think about unit, it's good. Here, f has a unit of a derivative, so it's a velocity if x is a position. Here, it has a unit of a position. Keep it in mind. But otherwise, it's essentially the same. I consider f of two variables, time and space, and this general equation. And for this, we have seen the existence of a solution for a very general condition on f. We will not discuss the existence of a solution for this one, but there exists an analog theorem. We will just look at two special cases. So this is the most general. This is called not a differential equation. This is called a difference equation. Because it's discrete time, it's called a difference equation. But now we have seen, and there is a nice report about this, dynamical system. In the continuous case, it's not about this generality. Dynamical systems are only defined when there is no explicit dependence on T. This is called the autonomous differential equation. It turned out the same for discrete time dynamical system. If you look at the condition for discrete time dynamical system, we cannot also have this one. So I observed, I was not aware of this, but I observed dynamical systems are quite restrictive in the sense that they have to be autonomous. So it means in this section, that's why I call discrete dynamical system only this section and not the big title. And that at the end of the day, once you look at dynamical system, it means you remove this dependence. We are just going to deal with iterated maps. So it's a bit disappointing. Still, there are many things to say in this framework. So as for the continuous case, dynamical system, with the definition I have given a long time ago, dynamical system deal with autonomous equation only. Autonomous means M, the dependence on M here cannot appear. So it means we are given to this equation, x of m plus 1 is f of x of m. But now you can iterate. X of m is f of xm minus 1, which is f of x minus 2. So it means this is nothing but f power m plus 1 of x0. Be careful what means this f power m plus 1. It means you apply f, then you apply f, then you apply f again. So it's not a power of a function. It's an iteration. Maybe I will not use this equation, this notation, but I think some people write like this. Just to emphasize this, okay, this is not a 0. This is the circle for composition. It's a you iterate, so it's a composition. All right, so essentially we have the solution. While it was quite complicated here to know that there exists a solution, here x of m plus 1 is given by the m plus 1 iterate of the initial condition, right? So I can define the flow, but it's essentially just a rephrasing. So in this case, the flow is defined by, so the flow is this phi. It's defined on g times m with value in m. And how we define it, if we take a small m, oh, sorry, it's a bit annoying that this is space, this is a variable for time. I had not thought about this. Goes to phi of mx. This is a flow, and this is nothing but f composed m times evaluated at x. This is a flow. It means starting with any initial condition, the flow gives you obtain the flow for any initial condition by applying f m times. So once you have the flow, it means this set g times m, what was it? No, it was gm phi is a dynamical system. You can check the definition of a dynamical system. It respects the conditions. So any g which is n or z any M which is a subset of Rn or of a metric space, phi given by this is a dynamical system. It's a discrete time dynamical system. What is a baby example in this case? Just a linear map. This is the simplest example. Still, it's already quite rich. This is the one you study in linear algebra. So M is Rn, and f of x is a matrix applied to x with a fixed matrix in Mn of R. So it means, in this case, Fm, so Xm, X of M, probably I should have written, yeah, no, this is correct. If it is a power M x0. So this is the easiest dynamical system. You just apply m times to an initial condition. Yes. If M is Rn, you are right, I could have written X is an element of Rn. It's a point in Rn. Yes. And you look at its evolution. So you take one point in R2, then you apply A, you get a different point, and I will speak about this. But this is a very simple example. We can do it explicitly. You just iterate a matrix. And with the Jordan normal form, it's even simpler because you can compute this explicitly. Right? So this is the simplest example of a discrete time dynamical system. So let me review. I will review some definition and introduce for both discrete and continuous dynamical system, but it's good just to review them now in the discrete time case. Review of some notions. So we have already seen them, but I just now make them more special for discrete time. So what is the orbit of x? So we have a x in M. What is the orbit of x? This is simply the phi of mx for any m in G. Remember, G is either n or z. These successive points. So an orbit is now no more continuous, it's made of discrete points. And if G is Z, it implies that in order to be consistent, we have that f of minus m has to be equal to f of minus 1. And so it implies that f has to be invertible. So whenever you have a dynamic discrete time, when you have a discrete time dynamical system on Z, you can only have it if it is invertible. You can go backward. So it means f for minus or negative number is this inverse map times m, or compose m times. No, m in n. So if it's not invertible, you can only define it on the half lines on n. A fixed point in our setting here, again, there is a small difference with this continuous time, so fixed point. What is the equation for fixed point? fixed point. It's simply x is equal to f of x. A fixed point. You are thinking about the asymptotic of orbit. So a fixed point satisfies this equation. By definition, it's a fixed point. The orbit is only one point. This is the way I define a fixed point. Its orbit is just one point. And what is n-periodic orbit? What it is a point x satisfying. No, not, sorry, n-periodic point. Orbit comes just after. N-periodic point, it's a point x satisfying that fn of x is x. So if you look at this picture, it means I start here, I go here, here, and let's say this is a 3-periodic orbit. Of course, I have a, so n is an integer, positive integer. There is a small condition. N should be the smallest one. I don't want to say that this is a 6-periodic orbit. It is also a 6-periodic orbit, but I don't want to look at this as a 6-periodic orbit. So I have to put a minimal condition. So we assume that Fm, sorry, this is a clash of notation, yellow M or red M. F, it has nothing to do with the M, which is a subset before. It's simply an integer. Fm of x should not be equal to x for any m in the set 1, 2, up to n minus 1. This is the only time I'm going to use capital M. I don't want to consider this as a 6 orbit. It's only a 3 orbit, 3-periodic orbit, 3-periodic point. So now I define this is a 3-periodic point, but as we will, as it's visible, as soon as I have a 3-periodic point, in fact, I have 2 other 3-periodic points, because this one is also a 3-periodic point, and this one is also a 3-periodic point. So as soon as you have an n-periodic point, in fact, you have n of them, and they define an orbit. So these 3 points define an orbit. So I've just introduced so far the n-periodic point. And now I need to define an orbit. So the first observation is given one n-periodic point, given x n-periodic points. What are the other one? F of x, f of x up to f n minus 1 of x. I should not put a set, they are just points. These are also n-periodic points. And it's visible on this picture. I started with a 3-periodic point. I have a second one and a third one. And when I consider them together, so an x, f of x, up to f n minus 1 of x is the orbit, the n-periodic orbit. Defined by x. So it's very similar to the continuous case, except that before we had a kind of circle. Now we just have a set of n points. Any question about this? No. Yes, there is an order. If this is x, this one is f of x, and this one is f square of x. In a sense, there is an order. There is a first iteration, the second iteration, and after n iteration, you are back to the initial one. So yes, there is a kind of order. You cannot go up in arbitrary order on an orbit. And the same, by the way, two orbits cannot share one point. It's not possible to have another orbit containing these 3 points. There would be a contradiction. So orbits, like in the continuous case, cannot cross. Here crossing would be, they cannot share one point. You easily get...
Go around in one side.
No, but it's not possible because you have only one f. So once you are here, when you apply f, you cannot be both here and here. This is a contradiction. F gives you only 1 point. Okay. For one-dimensional system, there is a very common picture, and I hope you have all seen it. For 1D system, so it means if I consider Rn is just R, one has a certain representation. One has it's called a cobweb. Representation. If you have never seen this, it's good to spend 5 minutes on this picture. I consider it's one-dimensional, so I do it in 2 dimensions. This is the diagonal. And I plot the function f. The function f is just of one variable. So let me plot f. I take the standard picture. This is f. It's a function of one variable. And I can represent the evolution. How you start with an initial condition. So you start with the x0. This is my x0. Then I want to compute f of x0. So f of x0, I end up here. This is f of x0. So this is x1. Now, I would like to compute the f of x1. So the trick is, sorry, it's not a good, I just arrived here, so I don't want to arrive here. So let me cheat just a little bit. So let me take x0 here. Should be a bit better. So we have x1. Then I want to compute f of x1. So the trick is to use the diagonal. Why? Because the diagonal gives me here again x1. This is the same as x1. So I get the image of x1 here. So this is x2. So we have x of 2 here. Now I want to have the, if I plot again, I go to the diagonal, this is x2. So it means the image of x2 is going to be here. So we have x3 here. And so on. Now you have the image. Oh, I am on a periodic orbit. This is good. This is what I wanted, but I'm surprised. So this is, we are converging to a periodic orbit. Look, we started with x0, x1, then we have x2, then we have x3, and by chance, I'm back to x2. So this, it's not a periodic orbit, but it's converging to a two-periodic orbit. So look, once I'm here, this is a two-periodic orbit. So by chance, I converge to a two-periodic orbit. So these 2 points, this is a two-periodic orbit. and I've converged quickly to this two-periodic orbit. So who has never seen this kind of picture? Is there anybody who has never seen this kind of plot? No, this is, yes, there is a mistake. Yeah, you have never seen. Why? Really? No.
Yeah.
You can play with this a lot. And I put some pictures in the notes. Okay, you surprised me. Sorry? Really? So if you haven't seen, please look at the note. Just Google this cobweb, and you will see plenty of pictures. For one-dimensional system, it's very standard. Now in the note, I've put a question. I haven't found so many examples of two-dimensional system. And I would be interested in having a report with an example of a two-dimension. Of course, it wouldn't look like this, but a nice two-dimensional dynamical system. No, it's not linear. This is clearly not linear. No, linear would be too easy, especially for you. So no, I don't want a linear one. A linear one, of course, you take a 2x2 matrix and you iterate. No, please do something more complicated. No. Okay. No, it wouldn't be. Indeed, this is specific to one-dimensional. You can use this picture only for one-dimensional. And of course, no, you can do it in 2D. You define this kind of pictures, but with an explicit and with an interesting example. So an example where you may have some periodic orbit, but maybe somewhere else you have a orbit going to infinity. So I expect more a picture of this type. But for a given f, something of this type. You can probably find some in the literature, I'm sure, but quickly I couldn't find. All right, so it's good we have this two-periodic orbit, and we have seen that, in fact, we converge to this two-periodic orbit. So let me use this. A point, I come back to the general setting. I'm not only in one dimension. So a point x in M converge to a n-periodic point. This is, be careful here, this is interesting. N-periodic point with, of course, n is always an integer. It's not that the limit m goes to infinity of fm of x is equal or exists. This is not correct. Be careful about this. If it converges to an n-periodic point, you cannot just say this, because this would mean it converges to a fixed point. An n-periodic point means you have to multiply by n, because you have to do steps, or you have to walk n time in order to be back to the same point. So it converges to an n-periodic point if limit m is an integer, but you compute fmn, or m capital N of x, and this limit has to exist. So be careful about this. It's quite natural. And it has to exist and belongs to. Okay. Yes, you had a question?
Multiplying factor n, and you take the limit different from m going to infinity alone.
Yes, it is. Oh yeah, look. This point, I cannot say it converge to either this point or this point. Because, so there is no limit. On the other hand, if I take square, if I take f square, I'm going to go always to either this point or this point, because I do 2 iterations. So no, it's not at all the same. So be careful about this. I told you, you think about this, it's completely natural, but the same for periodic orbit. The same for periodic orbit. We say an orbit is converging to a periodic orbit. We don't say that it's only converging to one point on this orbit. So it's something similar. It's not exactly the same, but the first thing which came to my mind. Still in this setting, so more generally, I told you it's a review. I defined W plus of a certain set lambda. So for lambda invariant, we define this as before the set of X in M, such that the distance between Fm of X and lambda is 0 in the limit M goes to infinity. So now it's a bit better than what I wrote before, because now so now lambda can be this 2 periodic orbit. It's not only one point, it's a 2 periodic orbit. And indeed, the distance between the initial point and this periodic orbit is going to 0. So this is better. And this is called as before, the stable set of capital omega, of capital lambda. And if this W plus of lambda is open, we call lambda attracting as before. So it's the same thing. Now, what about stability? So cobweb diagram, indeed, you should think about them. They are very useful. What about stability? So let me draw again my 3 periodic orbit. Be careful, it's only 3 points. I do this arrow just to tell you that I go from one to the other one, but it's not a continuous orbit. It's just 3 points. So you can wonder, oh, what about a point here? Is it, after iteration, is it becoming closer? So I should give a number 1, 2, 3, 4, 5, 6. Is it becoming closer to the periodic orbit, or is it moving away? This is a natural question. And this is, again, something you can solve with the Jacobian matrix. So as for the continuous time case, the stability near n periodic orbit can be studied with the Jacobian matrix. But be careful about one thing. It's the Jacobian matrix. Is it the Jacobian matrix of F? If I want to study the stability around this point here, yes, I need to compute the Jacobian matrix of Fn. and it's 3 in this example, because this point is a stable point for Fn, not for F. For F, I move from here to here. If I want to study the stability around this point, so what happens for points here, I need to compute the stability of Fn, so the Jacobian matrix of Fn at a point X. And now we know the story. If we compute this Jacobian matrix, we look at its eigenvalues depending if the eigenvalues. Oh, now there is a quiz. Should I consider the real part of the eigenvalues or if the eigenvalues are inside the unit circle? I told you before, depending if you study one matrix or the exponential of this matrix, there is a difference. So here, is it the eigenvalues which should have a real part which is negative, or should it be the one with inside the unit circle? No, it's here in this case. If you look carefully, it's inside the unit circle. And this is related to what I told you before. For the continuous case, F has a notion of derivative. For the discrete case, so this is a continuous case. For the discrete case, it's not like a position. So here, of course, on a concrete example, you will easily see it. But it depends if the eigenvalues are inside or not the unit disk of C. Yes. F, I assume at the beginning, F is still C1. I hope I mentioned it, but yeah, probably. Okay, you are right. If I didn't mention F, even if it is discrete, F is, because I want to have the flow on all points. You are right. Maybe I did not mention that F is C1. So if I didn't mention it, probably it's written in the notes, but I might not have written it here. Yes, F is C1 in order you are right to take the derivative. All right, so studying near a periodic orbit, it's the same as near a periodic point, but you need to do it for Fn. Now I see it's time. And by studying its eigenvalue of the Jacobian matrix, you get the stability. If they are all inside, if they are all outside, it's repealing. If some are inside, some are outside, then it depends on the direction. So I finished this review. I will just say a few more words. Next time we will introduce I will record so you can look at it. I will define a second type of dynamical system, which is not dynamical system, but it's still a discrete time evolution. And then I will concentrate on one concrete example, which is this logistic equation. So I will explain this in the recording. But it's good if you haven't seen this web plot before, it's cobweb, not webplot, then it's good to look at it. Okay. If you have any question, you can ask me. Otherwise, we meet again in 2 weeks, and I will send you a message tomorrow or the day after. Thank you.